Good evening, students. Today, let's start up with next theorem, condition of integrability. And this theorem states f belongs to R of alpha on closed interval AB if and only if for every epsilon positive there exists a partition P such that u of p comma f comma alpha minus L of p comma f comma alpha is less than epsilon. So f belong to R of alpha means if f is Riemann-Stieltjes integrable, okay, f is Riemann-Stieltjes integrable on closed interval AB if and only if for every epsilon positive there exists a partition P such that the difference between upper and lower sum is less than epsilon. So this is the condition of integrability. Okay, now let's get into the proof. For every partition P, we have this inequality. Okay, so this inequality holds for each and every partition P. What is that actually? L of p comma f comma alpha is less than or equal to integral a bar b f d alpha. That is, this is lower Riemann-Stieltjes integrable. Okay, and this is upper Riemann-Stieltjes integrable. And in previous theorem, we have learned lower Riemann-Stieltjes integrable is less than or equal to upper Riemann-Stieltjes integrable. So this inequality is from the previous theorem. Okay. Then how about this inequality? See here, this is nothing but lower Riemann-Stieltjes integrable. L of p comma f comma alpha is less than or equal to lower Riemann-Stieltjes integrable. What is the definition of lower Riemann-Stieltjes integrable? Actually, that is supremum of all lower sum. So, since this is the supremum of all lower sum, obviously this will be less than or equal to this. And coming to this inequality, this upper Riemann-Stieltjes integral is actually the infimum of all upper sums. So obviously this will be less than or equal to u of p comma f comma alpha. So this is all about the first inequality and name that as equation 1. Okay. And here I have assumed the second part. See here, let's assume this difference is less than epsilon and we'll prove that f belongs to R of alpha on closed interval AB. See, since there is if and only if, we need to prove in either ways. We need to assume this and we need to prove this. And conversely, we need to assume this and we need to prove this. Okay. So here, first we'll assume this and prove this. Okay. So, let u of p comma f comma alpha minus L of p comma f comma alpha less than epsilon. So, let's assume this first. Okay, and let's prove f belong to R of alpha and name this equation as 2. And from equation 1 and 2, this implies, see here, actually this one implies this integral minus this integral is less than or equal to up comma f comma alpha minus L of p comma f comma alpha. Okay, so this implies this minus this is less than or equal to this minus this. And we know that this minus this is less than epsilon. So, I have written this minus this is less than epsilon. And since this is less than or equal to this, the difference between this and this will be greater than or equal to 0. So, this is how it is. 0 less than or equal to upper Riemann minus lower Riemann-Stieltjes integral less than epsilon. And this equation 2, this one, is true for every epsilon positive, means epsilon can be chosen arbitrary here. Okay, so equation 2 is for every epsilon greater than 0 or every epsilon positive. Therefore, this becomes equal to this, because since epsilon is arbitrary, I can choose it as 0.00000001. Okay, so since that is arbitrary, I can choose the number which is very close to 0, very, very close to 0. So in that case, these two become equal. Okay, so that is how this upper Riemann becomes equal to lower Riemann-Stieltjes integral. So if these two are equal, then we say that f belongs to R of alpha. Conversely, suppose f belongs to R of alpha and epsilon greater than 0 be given. Now we need to prove that the difference between upper sum and lower sum is less than epsilon. Okay, and for this, let's consider two partitions P1 and P2 such that the difference between u of P2, f, alpha and integral a to b f d alpha less than epsilon by 2. See here, see from that equation 1, see here from equation 1, we have this. This is less than or equal to this, and this is less than or equal to upper Riemann, and upper Riemann is integral equal, less than or equal to upper sum. And here, since we are having f belongs to R of alpha, these two will become equal. And I can write that value as integral a to b f d alpha. So the same way I have written here, see this one, L of P1, f, alpha less than or equal to integral a to b f d alpha, and that is less than or equal to u of P2, f, alpha. And from this, I can, since this is less than or equal to this, I can write that the difference between this and this is less than epsilon by 2. Okay. And similarly, since this is less than or equal to this, I can write the difference between this and this is less than epsilon by 2. So this is what I have written. And now let P be the common refinement of P1 and P2. Okay. And let that P be equal to P1 equal P2. Okay. So if this is the case, then u of P, f, alpha less than or equal to u of P2, f, alpha. See here, P is the refinement of P2. Okay. And therefore, u of P, f, alpha is less than or equal to u of P2, f, alpha. And this u of P2, f, alpha is less than, see here, we have taken this difference is less than epsilon by 2 means if I take this integral minus integral f d alpha this side, I'll have u of P2, f, alpha less than integral f d alpha plus epsilon by 2. Okay, so I will write this is less than this plus this. So here less than integral f d alpha plus epsilon by 2. And this integral f d alpha plus epsilon by 2 is less than L of P1, f, alpha plus epsilon. See here, I have used this one. Okay, see here, if I take this minus L of P1, f, alpha this side, I have integral f d alpha less than epsilon by 2 plus L of P1, f, alpha. But now I have integral f d alpha plus epsilon by 2. So what I will do, I will add epsilon by 2 on both sides. So then I have integral f d alpha less than L of P1, f, alpha plus epsilon by 2 plus epsilon by 2. See why? Because see, this integral alone is less than this plus this. Okay, so if I add epsilon by 2 to both sides, then I have integral f d alpha plus epsilon by 2 is less than this plus extra epsilon by 2. So this epsilon by 2 and epsilon by 2 will become epsilon. So here integral f d alpha plus epsilon by 2 is less than L of P1, f, alpha plus epsilon. Okay, and this is less than, see this P1 is actually the subset of P. So P is the refinement of P1. So therefore, we know that L of P1 comma F comma alpha is less than or equal to L of P comma F comma alpha if P is the refinement of P1. Okay, so I have used that result and I have written this is less than or equal to this plus this epsilon. This epsilon I have written as it is. Okay, so this is less than or equal to this. And now this part, first part, and is less than this one, L of P comma F comma alpha plus epsilon. I have written less than and not less than or equal to, because I have less than here. I have less than here. Okay, so I have used less than. Okay, so now U of P comma F comma alpha is less than L of P comma F comma alpha plus epsilon. And if I bring this to the left hand side, I have U of P comma F comma alpha minus L of P comma F comma alpha less than epsilon. So this is the proof. Okay, thank you.